All right, welcome. Today we're cracking open the ultimate statistics toolkit. Yeah, we're going to gear you up to be a real data detective, ready to find all those stories hidden in the numbers. So let's grab that magnifying glass and get right into it.
I mean, have you ever wondered how Netflix just knows what you want to watch next? Or how a business decides, yep, this new product is a total hit? It kind of feels like magic, right? But it's not.
Well, the answer is statistics. But hold on, this is less about doing a bunch of complex math and way more about just asking the right questions. Think of it as a toolkit for being curious. Okay, so just like any good detective, you've got to know which tool to pull out of your bag for the job, right? In stats, the very first, most basic choice you have to make is whether you're going to use a parametric or a non-parametric method. And really, this all comes down to what you can assume about your data. So this first choice, it's a really interesting trade-off. Think of parametric methods on the left like a high-performance race car. They assume your data is perfectly behaved, following that classic bell curve. And if that's true, they are insanely powerful and fast. But what if your data is messy, or you've only got a small amount of it? Well, then you need the all-terrain vehicle on the right, non-parametric methods. They don't make as many assumptions, they work with things like ranks and frequencies, and that makes them way more flexible and tough. All right, let's grab our first tool and ask one of the biggest questions a data detective can ask. Are these things related? This is probably one of the most common things you'll do, trying to spot connections that nobody else can see right away. Okay, here's a classic business problem for you. You've got data on employee salaries and which department they work in, and you're wondering, is there a real link here? Are folks in engineering getting paid differently than the people in marketing? More than you just expect from random luck? This is exactly the kind of mystery a specific tool is designed to solve. And that tool is the chi-square test. Now forget the math for a minute, just focus on the logic. It's so simple. First, you observe what's actually happening. You count up your real data. Then you figure out what you'd expect to see if there was absolutely no relationship at all. And the last step, you just compare the two. The chi-square number is literally just a measure of the gap between what you saw and what you expected. If that gap is huge, ding, 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 you found a clue. Those two things are definitely related. But sometimes it's not enough to just say, yep, they're related. We want to know how they're related. So if you're trying to predict a continuous number, like say a house price based on its size, or what your sales are going to be next quarter based on your ad budget, the tool you're going to reach for is linear regression. Its whole job is to find the best possible straight line that cuts through your data to help you make those predictions. But what if your question is different? What if it's not how much, but is it going to happen? Will this customer leave us? Yes or no? Will this person default on a loan? Yes or no? See, a straight line just doesn't work for that. You might end up predicting a 150% chance of something happening, which is nonsense. And that's where logistic regression swoops in. It solves this problem by fitting this cool S-shaped curve to the data, which guarantees your prediction always stays nicely between 0% and 100%. Okay, let's switch gears a bit. We've been finding connections in the present. Now let's try to predict the future. And no, this isn't about crystal balls or anything like that. It's about using the patterns from the past to make a really smart, systematic guess about what's coming next. Now, before you even think about forecasting, you have to follow the golden rule, cross-validation. Okay, imagine you're teaching a student for a big test. If you just give them the exact questions and answers that'll be on the test, sure, they'll get a perfect score. But did they actually learn anything? Nope, they just memorized. That's what we call overfitting in data science. Cross-validation stops that from happening. You split your data. You use the training set to teach your model the ropes, and then you test it on the testing set, data it's never seen before, to see if it really gets it. So how do these forecasting models actually learn? Well, they do it by breaking down time-based data into its key parts. First, they look for a long-term trend. Is there general upward or downward movement over time, like a company's sales growing year over year? Second, is there seasonality? These are the predictable cycles, like ice cream sales going through the roof every single summer. And finally, there's autocorrelation. That's just a fancy way of asking, does what happened yesterday help you predict today? For things like stock prices, you bet it does. Finding connections and predicting the future, that's all great stuff. But the whole point is to use those insights to make better decisions. This is where statistics goes from just being about analysis to being about taking action, especially in a field like quality control. Look, in the real world, no test is ever perfect.
And that means you can always make one of two big mistakes. A type 1 error, that's a false positive. It's when the alarm goes off, but there's no fire. In manufacturing, that means you scrap a perfectly good batch of products. You just wasted money and resources. But a type 2 error, a false negative, that's when you miss a real problem. That means you ship a bad batch out to your customers, and that costs you your reputation, maybe even their trust. So managing any process is always about balancing the risk between these two kinds of errors.
So how do you manage that balancing act? You use a system called Statistical Process Control, or SPC. Its entire job is to be a watchdog for your process. It helps you see the difference between the normal, everyday, expected variation and a real signal that something has gone haywire and needs your immediate attention. And the main tool for SPC is the control chart. I want you to picture a highway. The center line is the middle of your lane. That's your process average. The upper and lower control limits, those are the guardrails on either side. Now, as long as your data points are just bouncing around between those guardrails, everything's fine. That's just normal, expected variation. But the second a data point flies outside those limits, bam, an alarm bell goes off. That's what's called a special cause, and it's a signal telling you to pull over and figure out what just went wrong.
Okay, we've been focused on the what and the why, but I want to give you a quick peek under the hood at the actual math, the engines that make all these tools work. Don't worry, we're not going to do any calculations. We're just going to appreciate the engineering. Here it is, the chi-square formula. And you can see our logic right there in the letters, can't you? It's literally just calculating the difference between O, what you observed, and E, what you expected, and then adding it all up. That's it. That's the little engine that measures the gap for us. Now, this one might look a little intimidating. I get it. But this formula is the whole secret behind logistic regression's magic. This is the mathematical function that takes all your messy data and elegantly squeezes it into that beautiful, predictive S-shaped curve, making sure your probabilities always land perfectly between 0 and 1. And finally, the engine for making smart bets when you're not sure what's going to happen, expected monetary value. It's so simple but so powerful. For every possible thing that could happen, you just multiply its payoff by the probability that'll happen. Then you just add them all up to find the smartest path forward.
You know, there's this quote from Carly Fiorina that just nails the whole point of this toolkit. The goal is to turn data into information and information into insight. That's exactly it. We don't use these tools to get numbers. We use them to turn raw data into useful information, and then to turn that information into a real, powerful insight we can act on. So that's what I want to leave you with. With these tools in your hand, tools for finding relationships, for seeing the future, for making better decisions, what hidden story is your data just waiting to tell? What's locked away in there, just waiting for a good detective like you to come and find it?